either people are really excited about it or they're really terrified of it. Those are it seems to be the two responses.
I've been working on AI for 3 decades, and I first started thinking about AI when I was a little kid in the late 60s and early 70s when I saw AIs and robots on the original Star Trek. So I guess I've had a lot of cycles to process the positives and negatives of it, whereas now, like, suddenly most of the world is thinking through all this for the first time. Now we're at a time in history when a lot of these ideas can be made real, which is amazing and scary. Not only are we on the cusp of creating a form of intelligence going beyond ourselves, but what kind of intelligence it is may depend on what the early stage AIs we're building now are actually doing and how they're organizing themselves. And we should make that as beneficial as we can.
He does it with a bit of a smile, right? I should do that too. Good to go. The following is a conversation with
Ben Goertzel,
who is one of the most influential people in the field of artificial general intelligence and spearheads many famous projects such as OpenCog, SingularityNet, and Sophia the robot. We read the SingularityNet paper by Ben and his collaborators, and then listened to Ben's appearance on the excellent Lex Fridman podcast, and we knew we had to talk to him. By the way, if you are interested in machine learning and AI, we cannot recommend the Lex Fridman podcast highly enough. That guy is great.
The field of artificial intelligence was founded in the mid-1950s with the aim of constructing thinking machines. That is to say, computer systems with human-like general intelligence. Think of humanoid robots that not only look, but act and think with intelligence equal to and ultimately greater than that of human beings. In the intervening years, though, the field has drifted far from its ambitious old-fashioned roots. We should again be pursuing artificial general intelligence as a distinct effort from our current narrow approaches. Too many people in the AI community still succumb to the first step fallacy, which is believing that incrementally improving current AI systems will lead towards artificial general intelligence. Admittedly, we're still waiting on the AI community to converge on an idea of what a good AGI architecture might look like, and indeed convincing evidence that such an architecture performs better than a narrow AI system. Dr. Ben Goertzel is an artificial intelligence researcher, CEO and founder of SingularityNet, a project combining artificial intelligence and blockchain together.
Suppose my good friend Ray Kurzweil is correct, that 2029 we get AIs as smart as people. By 2045 we have AIs boundlessly more intelligent than people. We're going to find that any AI that has human-level intelligence is going to have some species of advanced reflective consciousness, but I mean, I'm open to other possibilities. Humans are distinct individuals with our brains trapped in our heads and communication only by language, which is very low bandwidth, whereas AIs can swap brain matter whenever they want to. They can join into Borg minds and then subdivide whenever they want to. So it's going to be more like one big AI mind network rather than a bunch of AIs in competition. It seems very plausible within a few years of getting to that human level AI, it's going to invent all manner of amazing new things.
Ben seeks to fulfill the original ambitions of the field, which is to actually create artificial general intelligence. He graduated with a PhD in mathematics from Temple University in 1990. And Ben's approach to AGI over many decades now has been inspired by many disciplines, but in particular, in my opinion, from human cognitive psychology and computer science. Now, today, Ben's work has been mostly theoretically driven. He thinks that most of the deep learning approaches to AGI today try to model the brain. There might be a loose analogy to human neuroscience, but they've not really tried to derive the details of an AGI architecture from an overall conception of what a mind is. Ben thinks that what matters for creating human-level or greater intelligence is having the right information processing architecture, not the underlying mechanics via which the architecture is implemented. Now, Ben thinks there's a certain set of key cognitive processes and interactions that an AGI system must implement explicitly, such as working and long-term memory, deliberative and reactive processing, perception, action, reinforcement learning, metacognition, and several others. Ben thinks that biological systems tend to be messy, complex, and integrative. Searching for a single algorithm of general intelligence is an inappropriate attempt to project the aesthetics of physics or theoretical computer science onto a qualitatively different domain. Now, on the introduction to the show, I slightly offended Ben by characterizing him as a GoFi researcher. It certainly wasn't my intention to offend him, and I don't see GoFi as a pejorative term at all. I mean, I actually meant that I thought he was a symbolist, which is somewhat synonymous with GoFi in my mind. But having studied more of Ben's work since, it's pretty clear to me that he's not a pure symbolist. He clearly is a little bit, but he's in the rare camp of being sub-symbolic on a discrete knowledge graph. Now, sub-symbolic, it just means that abstract concepts should be distributed or sliced over your knowledge substrate. So it's possible to be sub-symbolic even without using artificial neural networks. So this means, by the way, that Jeff Hawkins' hierarchical temporal memory, his HTM algorithm, is also a sub-symbolic system, even though the substrate itself is discrete. Now, MLST is really big on diversity of thought in AI, and we focused a lot on modern variants of GoFi or modern-day hybrid symbolism recently. As well as not liking the old-fashioned part, let's face it, I mean, all AI is old-fashioned, right? Ben associated the term with the idea that knowledge should be handcrafted by humans, and his mind went straight to the disastrous Psych project, the largest ever knowledge graph created by humans. And indeed, the knowledge acquisition bottleneck was probably the most significant failure of expert systems in the 1980s. Actually, most symbolists I know today, and even many back then, didn't believe in handcrafted knowledge stores. I mean, symbolists say that knowledge should be acquired through reasoning, deduction, or instruction, and learning in a few cases. Most agree that knowledge bases should only be seeded with a small amount of core knowledge. Ben agrees with Rich Sutton that the knowledge cannot be handcrafted, but Sutton also meant in his Bitter Lesson essay that the modular cognitive architecture of an AI system similarly shouldn't be designed by a human. This is where they diverge. Sutton thinks that we should trust in the blank slate and empiricist models to discover the optimal structure and architecture. Ben, on the other hand, thinks we should design a modular cognitive architecture using the knowledge that we've gleaned from cognitive psychology. So I said to Ben at the time that I project all AI researchers onto a kind of map or a vector space, which represents their research interests. And I had placed Ben onto that map on the basis of the podcast that I'd listened to and the papers that I had read from him. In that map, he was closest to Marvin Minsky and Gary Marcus, two people I admire greatly, by the way. And this is because I believe Ben's work is strongly influenced by cognitive psychology, formal logic, and the belief that mind should be a hybrid of symbolic and sub-symbolic. Ben also thinks that cognitive architecture should be handcrafted, with designs inspired from our knowledge of human cognition, and also they should be strongly modular. He thinks that the underlying knowledge representation should be multimodal, distributed, composable, and captured in a discrete graph. So Ben thinks that we should seed the knowledge graph to some extent, but it should be able to acquire most of its knowledge from reasoning, imagination, experience, and display strongly emergent characteristics. So my map of AI researchers is probably wrong in many ways, but we all have an internal mental map that we use and update all the time. I mean, in my map, I think of empiricists like Jan LeCun, or logic, philosophy, and formal language folks like John McCarthy, or psychology folks like Gary Marcus, and even linguistics and cognitive science folks like Chomsky and Hofstadter. Some folks like John Searle and J. Mark Bishop, who we had on the show, don't think that AI could even exist at all. After the show, I asked Ben what he thought of my map, and he said he wasn't too impressed, actually. He quickly responded with his own better mental framework. He said that his dimensions were neuroscience, biology more broadly, so things like evolving ecosystems, or maybe even things like evolutionary algorithms or open-endedness, the general math theory of intelligence, so things like AIXI, formal logic, cognitive science and psychology, thinking of the human mind distinct from the human brain. Embodied action, so the kind of thing that Rodney Brooks would talk about in his subsumption robotics. Complex systems and nonlinear dynamics, the philosophy of mind, general systems theory, and also some of the applied empirical work, so the kind of stuff that we might be doing in robotics or automated theorem proving. He gave DeepMind as an example, so he said that they were motivated by the intersection of neuroscience and empirical applied work, and also the general mathematical theory of intelligence. So, Ben actually published a paper in 2014, Artificial General Intelligence, Concept, State-of-the-Art and Future Prospects, where he boiled down the spectrum of AGI designs into 4 even simpler categories, right? So, symbolic, emergentist, hybrid, and universalist. AGI theory is a patchwork of overlapping concepts and frameworks and hypotheses, often synergistic, but sometimes completely contradictory. So in this paper, Ben made some really insightful remarks about the nature of general intelligence, that it should be able to achieve a variety of goals and carry out a variety of tasks in a variety of different contexts and environments, that it should be able to handle novel problems and situations unanticipated by its creators. It should be able to transfer knowledge from one problem or context into another, and that arbitrarily general intelligence may not be possible given realistic resource constraints. He also pointed out that learning some tasks might be more efficient than others, and that humans display a higher level general intelligence than existing AI programs. And finally, it seems quite unlikely that humans happen to manifest a maximal level of general intelligence. So in the paper, Ben quickly introduced his core AGI hypothesis, which is that the creation of a general intelligence won't be on a continuum with narrow intelligences, that it's an entirely different category, although he does think there's some overlap. Ben said in the paper that there were 3 fundamental ways of characterizing general intelligence. There's a mathematical approach, an adaptionist approach, and an embodied approach. The mathematical approach was defined by Legg and Hutter with AIXI, and later their so-called universal intelligence conception of a computer program executed by an agent, achieving the best average reward, calculated over all possible environments, preferentially weighted to prefer the simplest programs. This kind of measure makes humans look quite dumb, and systems like AlphaGo look quite smart. Legg and Hutter argued that intelligence is purely a matter of capability and behavior, and independent of how much effort is expended. The adaptionist approach was defined by Pei Wang, and argued that artificial intelligence should be seen as adaptation to the environment, given limited resources. Ben released a paper in 2010 modifying Legg and Hutter's universal intelligence paper to account for the factors which Wang raised. Wang believed that the essence of general intelligence laid in the complex compromises needed to achieve generality using limited computational resources. The embodiment approach was similar to the adaptionist approach, but held the contention that intelligence is something that physical bodies do in physical environments. Rodney Brooks is the best-known advocate for this perspective. Ben cited another paper from Pfeiffer and Bernard to summarize this view. They said that the study of intelligence always seemed to boil down to compliance and diversity. Intelligent agents always comply with the physical and social rules of their environment and exploit those rules to produce diverse behavior. Animals and humans have gravity and friction to contend with. Advocates of the embodiment tradition argue that it makes sense to think about achieving human-like intelligence the same way evolution did it, which is to say, in the context of controlling a body with complex sensors and actuators in a complex physical world. Now, let's get to the punchline. Do you remember the 4 categories of AGI researchers that I promised to tell you about? Well, symbolic AGI advocates argue that symbolic thought is what most strongly distinguishes humans from other animals. It's the crux of human general intelligence. What allows us to generalize so broadly. The idea is that minds manipulate symbols representing aspects of the world or themselves. Generally, these architectures have an explicit knowledge base. They have short and long-term memory banks, and they have the explicit notion of perception, cognition, and action. Ben points out that symbolic architectures tend to be quite weak in learning, and creativity, and procedure learning, and even episodic and associative memory. Ben also points out that the line between symbolic and connectionism gets a little bit blurry with some algorithms because they produce massive and incomprehensible symbol networks, which are not too dissimilar to connectionist models in many ways. Ben also argues that a purely symbolist architecture seems to be incapable of giving rise to the emergent structures and dynamics required to yield human-like general intelligence. The emergentist AGI school of thought expects abstract symbol processing to emerge from low-level subsymbolic dynamics, perhaps a neural network or even a real brain. The human brain consists of a large set of simple elements, complexly self-organizing into dynamical structures in response to the body's experience. Ben says that no one has yet compellingly showed how to achieve high-level functions such as abstract reasoning or complex language processing using a purely subsymbolic emergentist approach. A pretty strong example of the emergentist approach is the cognitive neuroscience folks, right? So people like Jeff Hawkins. The brain is the only example that we have of a system with a high level of general intelligence. So emulating the brain seems like the most straightforward path to achieve AGI. So Jeff Hawkins' brain-inspired hierarchical temporal memory, or HTM algorithm, which we'll cover on next week's show, immediately springs to mind. And there have been many large-scale brain simulation projects. We actually interviewed Dr. Simon Stringer recently, who's building a brain-inspired and biologically plausible neural network at Oxford University. Even regular deep learning folks, they view their architectures as emergentist, hoping that scaling will lead to these kind of complex dynamics and emergent symbol processing. Ben says that the brain's cognitive mechanisms are well tuned to run efficiently on neural wetware, but are poorly suited for our computational hardware today. Now, onto hybrid AGI architectures. Ben would consider himself a hybrid AGI researcher, right? So advocates of hybrid architectures, they make the case that the whole is greater than the sum of its parts. I mean, Ben captures this idea with the phrase cognitive synergy, which we'll discuss at great length on the show today, but Ben's OpenCog system is one such hybrid AGI architecture. Most hybrid architectures are strongly modular in some sense, but that doesn't mean that we should think of the individual components as being entirely encapsulated black boxes. The levels of interaction depth between the modules actually vary depending on different architectural patterns. Ben thinks the design goal of a hybrid system is achieved when different parts work together synergistically, each module contributing its strengths to help others overcome their weaknesses. On the flip side, though, when you try to tie together qualitatively different modules, you get a brittle system that can't adapt very well because the different components can't work together with full flexibility. Now, the other week we spoke about neurosymbolic approaches to AI with Professor Gary Marcus and Professor Lewis Lamb. And when Ben talks about hybrid systems, I think he's mostly referring to their strong modularity and synergistic potential rather than the kind of dichotomy of symbolic and sub-symbolic knowledge representation. Finally, Ben says there are universalist approaches to AGI, which are distinct from the other three. It's the idea that AGI algorithms would yield incredibly powerful general intelligence if only we supplied them with infinite amounts of computing power. Advocates of this approach think that we should start at this level of abstraction and kind of work downwards rather than the somewhat bottom-up approaches that we just spoke about. Now, these approaches can be traced back to Solomonov's theory of induction, but perhaps these days are mostly thought of in respect of Marcus Hutter's AIXI system. Hutter thought that an AGI system would be controlled by some program, and we could search through the space of possible programs to find the one that would have worked best in all the previous situations that we encountered. And then we could just rinse and repeat this process with every new situation we found ourselves in. I mean, there's a bit of a no-lunch caveat there, of course, and that clearly it will depend in some sense on the situation space that we've experienced rather than having kind of general utility. But it would be provably optimal for the situations that we have been in. It gets a little bit muddy, though, as it requires the notion of an arbitrary reward function, which is linked to the environment. By the way, Schmidhuber's Gödel machine from 2006 was conceptually similar, and Ben even pointed out in the paper that achieving general intelligence with infinite computing power, it's just a mathematical game at the end of the day. I mean, it's only minimally relevant to achieving AGI using realistic amounts of resources. So when we say GoFi on MLST, we don't necessarily mean the AI zeitgeist of the 1980s. We mean modern-day symbolists, almost all of which advocate for a hybrid approach. The ideas are evolving all the time, right? The school of thought has recently been branded neurosymbolic, or the third wave, right? Most of these folks now embrace using neural networks as perception modules and the need to have empirical learning in addition to logical reasoning. Their mindset is, in my opinion, most characterized by the belief that AI systems should be strongly modular, that knowledge should be represented explicitly and discretely, or at least mostly discretely, usually in some kind of graph, and they advocate for the primacy of logic-based reasoning for knowledge acquisition. It's worth also noting that Ben has been pretty harshly critical of neural networks. In particular GPT-3 and its apparent lack of understanding. Ben frequently cites Marvin Minsky's Society of Mind as one of his inspirations. How can intelligence emerge from non-intelligence? Well, Marvin Minsky thought that it was possible to build a mind from many small mindless parts.
One possibility I've been working toward a lot lately is what AI pioneer Marvin Minsky had called the Society of Minds, which is also an economy of minds. The idea that it may not be one algorithm written by one guy or one program written by one company that gives the breakthrough to general intelligence and then superintelligence. It may be a network of different AIs, each doing different things, specializing on certain kinds of problems, some of them specializing in generalization and abstraction, and maybe this network of AIs cooperating together, forming sort of emergent intelligence, maybe how we get the breakthrough. You could think of this as a global brain. I think it's almost inevitable by this point that humanity is going to create synthetic intelligences with tremendously greater general intelligence and practical capability than human beings have. I think I know how to do that with the software I'm working on with my own team, but if we fail, there's a load of other teams who I think are a bit behind us, but are going in the same direction now,
so
right?
You guys feel like you're at the tip of the spear with this stuff?
I do. We use a sort of neural symbolic knowledge graph. You use neural nets to recognize sensory data, and you use a sort of probabilistic logic for abstract reasoning. You use simulations of evolution processes to come up with new ideas. But, whether it's a deep neural net or an open cog system or one of the other many approaches being pioneered right now, what's cool is there's a lot of research teams working full-time on not just building narrow AI applications doing specific things, but trying to break through to artificial general intelligence.
OpenCog is a project that aims to build an open-source artificial intelligence framework. It defines a set of interacting components designed to give rise to human-equivalent artificial general intelligence as an emergent phenomenon of the whole system. OpenCog is a software framework which hosts multimodal cognitive processors on top of a common representational substrate, or in plain English, a common knowledge graph, which has been implemented as a graph database. The cognitive processors could in theory be anything, but we're talking about things like a discrete program search, or evolutionary algorithms, or neural networks, or probabilistic logic programming, and so on. This is a remarkable feature of OpenCog, that it provides a unifying substrate for a whole range of relational or logical analysis. It opens up the possibility for true hybrid analysis from the bottom up and the top down. OpenCog could in theory represent both neural and symbolic operations and then map logical reasoning and inference between them. So, for example, suppose we're training two natural language models in this framework, one classical computational linguistic style model, and the other one could be a kind of set of modern transformer type models. An OpenCog agent could compare the metagraphs back and forth between the methods and search for subgraph fuzzy isomorphisms and merge edges and weights between them. This has got the potential to guide the optimization procedure, unblocking the models from each other and possibly even sidestepping some of the exponential blow-ups which would have otherwise occurred. So, in the most basic sense, Ben thinks that we can transfer learning between different modalities of analysis, right? He thinks that we can effectively white box every type of analysis and represent it topologically. I think Ben's core vision is that there's some kind of topological similarities between all knowledge representations, and interesting things might emerge from them when we start to bind them together and form increasingly abstract knowledge representations. So this unified architecture, I mean, it has another advantage, in my opinion. It allows for decentralized agents operating on a common knowledge platform. I mean, imagine an agent which was responsible for encoding, I don't know, a mathematical theorem, wandering around the metagraph, finding subgraphs that match the theorem, and then adding the implied links. Or maybe a machine learning agent that encodes empirical statistical relationships between word phrases and then adding weighted association links to matching phrases. So overall, OpenCog presents a highly dynamic, almost organic platform for evolving knowledge and algorithms. I mean, it's easy to see Ben's optimism that AGI will emerge from this approach. I mean, we're a little bit more skeptical whether it will in practice. It all comes down to whether the faith in such emergence is just that. Is it just a faith, or could it actually happen? So, Ben is also the creator of SingularityNet, a decentralized open API marketplace for AIs built on blockchain. The implications are that it could let anyone monetize AI. Yannick made a video about Ben's SingularityNet a while back, so please watch that. I'll put a link in the description.
So SingularityNet is as it says, a global AI marketplace, but it is also kind of an effort. It is a foundation. It has blockchain in it. It has AI in it. It has symbolic computation. It has graphs. It has all the things, all the buzzwords you could possibly want. So the high-level summary of this system is that it is a marketplace for APIs, basically, on blockchain, where either humans or APIs can call other APIs and pay them for that service. And the goal is to sort of get a network going of APIs that call APIs that call APIs, and sort of have that build into a global AI, not only marketplace, but like as itself a global AI. This is backed by the SingularityNet Foundation, and they do a whole bunch of development of the platform, but also research on the platform.
I'll put a link in the description, but he did a pretty good job of walking through their recent white paper. Just before we kick off as well, make sure you check out Ben's new paper that he released very recently. It's called The General Theory of General Intelligence, a Pragmatic Patternist Perspective. The patternist philosophy of mind is a general approach to thinking about intelligent systems based on the very simple premise that a mind is made of a pattern. So a mind is a system for recognizing patterns in itself and the world, critically including patterns regarding which procedures are likely to lead to the achievement of which goals in which contexts. Intelligence can be partially conceived in this framework, he says, as the ability to achieve complex goals in complex environments, where complexity itself may be defined as the possession of a rich variety of patterns. A mind is thus a collection of patterns that is associated with a persistent dynamical process that achieves highly patterned goals in highly patterned environments.
So, I mean, I've long been an advocate of a philosophy I think of as patternism. Like, it's the pattern of organization that appears to be the critical thing, and the individual cells, and going down further, like the molecules and particles in our body are turning over all the time. So it's not the specific combination of elementary particles which makes me who I am or makes you who you are. It's a pattern by which they're organized and the patterns by which they change over time. So, if we can create digital systems or quantum computers or femtocomputers or whatever it is, manifesting the patterns of organization that constitute intelligence, then there you are. There's intelligence, right? So that's not to say that, consciousness and experience is just about patterns of organization. There may be more dimensions to it, but when you look at what constitutes intelligence, thinking, cognition, problem solving, it's the pattern of organization, not the specific material as far as we can tell.
So he talks about some of the key drivers to these dynamics, things like evolution and autopoiesis and association and self-structure. And then he goes on to talk a lot about cognitive synergy again. Anyway, it's a really interesting paper. Admittedly, it's got a lot of technical jargon in it. It's quite long, but I really do recommend you have a look at that because it's probably the most up-to-date thinking from Ben. Anyway, we had a really, really good conversation with Ben, and I really hope you enjoy the conversation as much as we did. And yeah, I hope I didn't piss Ben off too much by calling him a GoFi researcher. I'm sorry, Ben. Take it back. Enjoy the show. Peace out. Dr. Goetzel, welcome to MLST. We are so honoured to have you here. You're truly an enigma to me. I think you're a rare breed. You seem like one of the last standing GoFi researchers, but unlike all of the other ones, you're well funded, and to some extent, you've actually realised Minsky's vision. Now, GoFi advocates today talk about the need to represent different types of knowledge: declarative, procedural, episodic, sensory, intentional, and attentional. This knowledge is the dark matter of the universe of AI, but this is what you've already done in OpenCog. You've been an inspirational figure in the AI community for decades now. You're a walking, talking polymath and oracle. Keith remarked that he couldn't believe how much knowledge could reside in a single brain. You believe that the creation of advanced AGI systems is mostly an engineering endeavour, which will require significant input from science and mathematics, and also philosophy. Also, I think it's fair to say that there are more complicated sounding words in your papers than I've seen anywhere else, and you're also an aficionado of extremely long bulleted lists. So anyway, on to my first question. On your OpenCog page, you said that the secret source of AGI is cognitive synergy. You say that it's important that cognitive processes associated with different types of memory can appeal to each other for assistance in overcoming bottlenecks. The human brain appears to be an assemblage of diverse structures and dynamics, built using common components and arranged according to a sensible cognitive architecture. You say that their close interoperation gives rise to the overall systemic behaviors that characterize human-like general intelligence. The components richly and dynamically support and assist each other, and emergent structures and dynamics quickly appear. Now, this leads to your core hypothesis, which is that integrating multiple symbolic and sub-symbolic learning and memory components in an appropriate cognitive architecture and environment can yield robust human-like intelligence. In some sense, it seems like a reasonable thing to say. I mean, if you look at a typical corporation, few would deny that a Gestalt emergent intelligence forms on top of the society of individuals in that corporation. But the key question is why? I can intuitively understand why a superintelligence emerges in a corporation, or the human brain for that matter, but I cannot intuit why a superintelligence would emerge from Singularity Net. So what's your take on it, Ben?
So, first of all, I have to admit your introduction got my dander up a little bit, because I totally don't think of myself as a GoFi researcher. I mean, the reason I didn't do a PhD in AI back in the 80s when I did my PhD in mathematics was precisely that the good old-fashioned AI that was dominating the AI field at that time seemed to me to have nothing to do with intelligence in any way I was interested in it. I tried to do a PhD thesis on prediction of multiple coupled time series using asymmetric Hopfield nets, basically, which would now be like a plain vanilla master's degree or undergraduate course project, right? And no one would do it because it was too like neural netty and soft and weird, right? So I never felt any affection for what I took as the primary characteristics of GoFi, which were, the idea that the knowledge you could feed into an AI system should be fed in by human beings coding a bunch of expert rules in some knowledge base, like the Psych project tried to do and others before. Like that always seemed insane to me. So I mean, I've always been a huge fan of experiential interactive learning, of the idea that to get an AGI, a system has to recognize patterns in itself and its environment and figure it out as it goes, right? And
right.
In that sense, I felt the transition from the expert system methodology, which was a key part of GoFi back in the actual good old-fashioned days, the step from that to supervised learning was a smaller step than was commonly understood, because you're going from hand coding a bunch of rules to hand labeling or hand categorizing a bunch of data, which is in many cases a step forward, but it's still a far cry from this sort of, completely unstructured experiential learning that one might seek. And then of course, now the ML community is significantly going beyond traditional supervised learning. You have unsupervised, semi-supervised learning, and reinforcement learning starts to rise to the fore. So the mainstream of AI is getting closer and closer to experiential and interactive learning, but it's still not really there any more than GoFi was there back in the 70s or 80s.
Sure.
And this brings us to cognitive synergy, in that the need for cognitive synergy in an AGI system really comes out of the need to do experiential interactive learning, which involves achieving complex goals in a complex environment under fairly strictly limited compute resources. So if you don't have limitations on compute resources, you could argue the point in various ways, but there's well-known work by Marcus Hutter in his book Universal AI, with Jürgen Schmidt-Huber with his paper on Gödel machine. I mean, there's at least some interesting theoretical arguments that with supermassive compute power, you could make systems that solved all sorts of incredible complex problems in complex environments with really, 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 really simple algorithms. It could be like a dozen lines of Lisp code or something, right? But when you get into the sort of situation that human brains seem to evolve for, or into the sort of situation that we have when building actual systems now, I mean, actual AI or proto-AGI systems now, I mean, you're in a situation where processing power and memory are not anywhere close to what you would ideally like them to be, given the complexity of the tasks that you have. And that logically puts you in a situation where, if the multiple sorts of things that AI needs to do can overlap or reinforce each other in some way, you're going to make better use of those limited resources, right? And I mean, that very, very simple line of reasoning is the crux of cognitive synergy. But then you need to get into what are the types of knowledge and learning involved in making an human-like AGI system, or for that matter, a transhuman AGI system, which one would suppose would include even more kinds of knowledge and learning than a human-like AGI system. And there you get into like cognitive science and what are the kinds of knowledge that a human mind has, what kinds of learning are associated with those kinds of knowledge, which leads you on to the particular ways that cognitive synergy manifests itself in an AGI design like OpenCog, which sort of winds you back to good old-fashioned AI and neural symbolic AI. Because if you look at sensory or perceptual knowledge as one of the kinds of knowledge that the human brain evolved to deal with for the kinds of tasks and environments it had to deal with, it's clear that modern deep neural nets are one type of system that's really good at pattern recognition and huge amounts of sensory knowledge. If you look at declarative knowledge, like facts and beliefs, including more abstract ones, such as have been explored in the logic field, it's pretty clear to me that uncertain reasoning engines and various sorts of logic formalisms provide a good way to deal with this sort of abstract knowledge. So the cognitive synergy approach would say, in that particular example, take a neural system or something like that for dealing with masses of sensory knowledge, take something that's doing something like a logic system. I mean, it could be an appropriately structured neural net, or it could be a full-on logic engine to deal with the declarative and semantic knowledge. But then how do you couple them together so that you have a sort of perception, cognition, feedback that's not just two black boxes, right? But the two components are sensitive to each other's intermediate states while they're going through competition, so they can help each other cut through combinatorial explosions. So that's one example: sensory processing with neural nets and declarative knowledge processing with logic engines.
I don't want to go through all the examples now because that would make this answer super long, but that should give you a flavor.
That's fine. And look, I just wanted to clear up the bit at the beginning. So first of all, when I say a GoFi person, I don't mean that in any way pejoratively. We are really interested in GoFi on this channel. We have people like Gary Marcus
I get
on.
That, but I grew up thinking GoFi was an insult.
Well,
right?
no.
It's really,
first of all, I just
really
wanted.
funny to me that the field is wound around this way.
You have to see this from my point of view.
Not...
So we interview loads and loads of AI researchers, and I project them into a kind of vector space in my mind. You know, Pedro Domingo says that there's 5 tribes in AI, and you see evolutionary people and kind of logic-based people and it's kind of empirical people. So the reason why I placed you there in the vector space is you believe in the primacy of modularization and the society of mind, the primacy of knowledge, and also that systems should be discrete first. I agree with you 100% that knowledge shouldn't be handcrafted, by the way, and Rich Sutton. I mean, we're completely aligned on that. But you can see why, on the basis of those things.
Because my view of it would be that declarative or semantic knowledge is very effectively modeled as logical propositions in some logic, which may be an uncertain, paraconsistent, intuitionistic logic, and not the kinds of logic that people are most commonly dealing with. But I don't think that, say, the knowledge of what this coffee cup looks like is effectively well captured as a set of logical propositions. It's pretty clear that some continuous variable type model is more effective at capturing my sensory knowledge of what this coffee cup looks like.
Can I just append a little bit on that point, because you made a good point in that we have all these different systems, different types of knowledge. Some of them may be well captured by some continuous systems. Some may be well captured by discrete systems. They have to interconnect somewhere. Now, if you look at, let's say, the current trend, the current hype, I think that most people will go about this and say, of course, the space in which they connect should be some sort of a vector space, should be some sort of a distributed thing where we do, inner products to search for similarities and whatnot. Yet, if I understand you correctly, you've made repeatedly the case that good ways of interconnecting these systems is actually through graphs and through sort of graphs on graphs or hypergraphs. And could you maybe go into that a little bit? Why do you think that graphs specifically are good representations, or why should graphs be sort of the fundamental base where these different processes interconnect, if I understood you correctly in that?
Yeah, I've been an advocate of graph, hypergraph, and metagraph representations for AGI systems and narrow AI systems for a long time before it became fashionable with things like Neo4j and Kraken and so forth. I would say that the distinction of graphs versus vectors sort of points you in the wrong direction, in the sense that, I mean, you can represent a graph as a bunch of vectors, as an adjacency matrix or something, and you can also project a bunch of vectors into a graph if you want to. So, but the real question is, what operations need to be efficient on this set of knowledge, right? And I mean, most neural net algorithms in common commercial use today, they're based on matrix math, right? I mean, they're based on linear operations. You're doing inner products, as you mentioned. You're doing some dimension reductions, and then you're doing matrix multiplying and so forth. So I think that I don't believe that these sorts of linear operations on high dimensional vector spaces are the right algebra for most of what general intelligence needs to do. I mean, I used to teach computer graphics when I was in a much earlier phase of my career, and which is where the processing tools now used for AI come from. Believe it or not, young people may not realize it today, but GPUs used to be used for graphics, not just for machine learning, right? And so, I mean, what you see in computer graphics is the value of vector operations for dealing with images and visual data. And you have something similar in audio data. So I think these linear operations are more appropriate for this sensory data, which makes total sense because this is data coming from like the 4D space-time continuum, which has all these linear symmetries for the same reason that matrix symmetry groups play such a role in theoretical physics, right? And I think when you get on to more abstract cognitive operations or to procedural knowledge, say to do complex motor coordination or something, I think these linear algebra operations are less critical. Not that they're useless, but I think they play a less central role. And when I early in my career declined to do a PhD in AI because I didn't like the sort of hand-coded expert production system direction that the AI field was sort of hypnotized by at that point in time. What I got deeply into was nonlinear dynamics and chaos theory and self-organizing systems. And I feel like that's something that's very much missing in the modern approach to AI with deep neural networks. So when I taught neural networks in the mid-90s, when I co-founded the cognitive science program at University of Western Australia, where I was a professor, I mean, we had a big focus on, we did Rumelhart and McClellan stuff with like parallel distributed processing and multi-layer backprop, which were deep neural networks, right? But we did Hopfield networks and asymmetrical Hopfield networks that can organize into strange attractors, recognizing patterns in data and how to do things. And it seems like this nonlinear dynamical aspect has not yet been relearned or regained within the neural net paradigm as it's become mainstream. But it ties in with why graphs are useful, because if you have a complex body of knowledge and you have a bunch of nonlinear transformations that you want to carry out, perhaps in an asynchronous parallel way on this large body of knowledge, a graph, or better yet, a hypergraph or a metagraph, are a relatively concise and efficient way to organize knowledge that will allow you to efficiently execute a variety of these nonlinear operations. It's quite different than wanting to multiply a matrix by a vector, although you could convert back and forth between the graph and vector representations if you want to.
I have a question about that. So let's for the moment suppose that that's all correct mathematically. I'm sure it is, that a hypergraph is a very good implementation substrate for efficient, calculations of that sort. Is it fair to say that the brain, because in the brain, when a neuron pulses, that pulse will travel to all the connected, downstream neurons, so that's effectively a hyperedge, right? And at the same time, axons can sometimes connect back to, say, long dendrites, which are themselves a link, and so it can kind of mediate that link. So is it fair to say that the brain does implement at that level a hypergraph or a metagraph?
In a way, dendritic connections are like hypergraph connections, right? I mean, you have a connection going to a dendrite, which modulates what flows on that dendrite. But I wouldn't want to overstate that too much, because I guess I tend to think the brain is a quite complex, continuous variable quantum chemical system that we barely understand. And you have glia doing a lot of stuff in memory. If you look at Eugene Izhikevich, who you should interview if you haven't, Eugene Izhikevich, who's now running Brain Corporation. I mean, he had a book decades ago on the geometry of the neuron, where he looked at the nonlinear dynamics of flow through a neuron. And he showed that even when you have a network of neurons simulating hippocampus, even if none of the neurons fire, that the slow wave dynamic from the Hodgkin-Huxley equation causes phase coordination in the whole network, right? So there's charge diffusion through the extracellular matrix, through just these water megamolecules floating around in the brain. And what role does that play in, say, solving the binding problem from cognitive science, or in in unifying parts of the brain into what's reported as a state of consciousness. I mean, I feel like, yeah, definitely there's some hypergraph structure in the brain. And Henry Markram published a paper showing this funky higher dimensional algebraic topological structure in the brain. But there's probably a lot of other totally different funky stuff going on in the brain that we haven't yet penetrated to. And it's that's all really cool. Like, I mean, much earlier in my career, I thought, like, should I try to figure out how to build a mind just by semi-ad hoc integrating knowledge from all different areas of intellectual pursuit? Should I try to make a cosmic mathematical theory of how intelligence works? Or should I just invent a better brain imager so we can measure what the hell is actually happening in here, which may bear no resemblance to what current neuroscience thinks? Because I remember in the 90s when I was in cognitive science department arguing with the neuroscientists who didn't believe in synaptogenesis or neurogenesis in adult brains. They're like, no, this doesn't happen. And now, now those things happen, but there's a lot of other stuff that they say just can't happen, and we just don't know. Well, so that's I'm more bullish on modern neural nets just as cool algorithms to do stuff than as having too much to do with how the brain works, which is fine. I mean, an airplane doesn't have to flap its wings to be good at flying either.
Sure, but as you kind of pointed out earlier, we can often get extremely valuable inspiration and insight from looking at the sort of only known, generally intelligent, if we want to call it that, system that we have. And you mentioned one earlier, which is, in your view, the kind of deep learning paradigms right now have lost the complex, nonlinear sort of temporal dynamics that take place in the brain. So I'm just wondering if you had to choose a handful of, say, abstract properties of the human brain, 1, 2, or 3 things that you think we need to fold back into the modern paradigms to make significantly more progress, what would it be? What's missing right now? Would it be those complex nonlinear temporal dynamics or some other features? Or
well, an awful lot of things are almost. I mean, if you're saying what's missing from modern neural net architectures, almost everything.
Yeah, what's missing? But the top few
10%
things that are
what's
missing
known in the human brain. I mean, I think so that deep neural networks that are most commonly used for sensory data processing are, you could view as a crude model of the feed-forward processing of visual or auditory cortex. And they capture pretty well what happens within the first half second of visual or auditory perception. Then when something takes you longer to sort of scrutinize and figure out what it is you're looking at, what's happening there, vision is feeding through to cognition. Cognition is feeding back to vision. And you have a nonlinear feedback dynamic there. And I don't think we're really capturing that in the neural networks used for sensory data processing. And instead we're going in a different direction, and we're feeding massively more data than any individual human has seen into an algorithm, so that the feed-forward processing can do in these algorithms what the human brain needs feedback processing to achieve, right? So it started out as a model of feed-forward processing of visual and secondarily auditory cortex, and then it went in a different direction based on exploiting what was possible with data sets and hardware available, which is certainly cool. I mean, I think if I was going to highlight 2, or let's say 3 abstract properties without going through a list of all the hundreds of neural assemblies that are not modeled in current AI architectures, we want to look at 3 abstract properties. So we're not capturing attractor formation and nonlinear dynamics. Like, go back to Walter Freeman's work on rabbit brains from the 1890s, showing that rabbit olfactory cortex recognizes smells by strange attractors, or Gary Lynch's work showing that the cognitive parts of the cortex largely evolved from reptile olfactory bulb rather than video or auditory cortex. I mean, we're not getting attractor formation, because that's just not what we're trying to do. What Gerald Edelman explored in his work on neural Darwinism, and he was a collaborator later of Eugene Izhikevich, whose work I mentioned on the nonlinear dynamics of the neuron. Neural Darwinism was a theory of the evolution by a sort of natural selection of neural subassemblies. I mean, we're not capturing that in modern neural architectures at all, and simplistic attempts to use CMAES or other evolutionary algorithms to evolve neural nets are not the same, right? I mean, and then we're not getting what my friend Weaver, aka David Weinbaum, called open-ended intelligence in his PhD thesis at the Free University of Brussels, which is the ability that the brain, the radical level of plasticity that the brain can show. Like my mother's partner lost 30% of her brain in a car crash. Literally the first year after that, she thought people were chickens. I mean, she didn't know idea what the fuck was going on. She regained essentially all functions, but lost some traumatic memories from her youth. But there was like radical rebuilding in the brain. And this ties in with goal systems also, right? Like, to what extent are we goal driven? I mean, yeah, we want sex, we want food, we want status, we want to have fun. But in the end, a lot of our activities are not too goal driven in any comprehensible way. And we're even able to rebuild our own goals as part of this whole evolutionary nonlinear dynamic that our brains are going through. So there's a lot missing at that high level, and then you go in to the fact that we're not really modeling most of the cortex, or how the cortex interacts with the thalamus or the basal ganglia or tectum or so many other parts of the brain, which like what Demis Hassabis has been after is at Google DeepMind and before is cortex hippocampus interaction, and he has very interesting ideas on that. But that's like one binary interaction among many dozens of things you could look at if you're trying to make a serious model of neuroscience, which I'm not trying to do, although maybe there's some parallel universe version of me trying to do it. It's certainly cool.
Could I come in on a couple of things there? So you were talking about the whole goal-driven aspect of AI, and we want to get to AIXI a little bit later. But on the modularity of the brain, that's interesting as well, because as you say, some people could suffer from a stroke, but they seem to regain a lot of their brain. We spoke to Jeff Hawkins a couple of weeks ago, and his thesis is that the brain is a general learning algorithm, and that's one of the reasons why the neocortex can be repurposed to do different things in the event of a stroke. But I want to pick up on something you said a little bit previous to that, which was about perception being a kind of low-level only process. So when we talk about different schools of thought in cognitive architectures, you said on Lex's podcast that you were surprised that trivial systems, your words not mine, like deep reinforcement learning, could work so well, and we should learn from them. Minsky conceived a modular architecture, the society of mind, and a lot of symbolists assert that reasoning must be separated from perception. They think that the only reason we need a perception module is to create a representation so that we can do the real reasoning downstream on some abstract knowledge representation. But I think you're a really interesting character, Ben, because you say we have sensory knowledge, and presumably the kind of reasoning we perform on sensory knowledge would be different to other types of knowledge. But having said that, I kind of agree with Melanie Mitchell, who said that visual reasoning isn't easily separable from the rest of intelligence, especially general knowledge and abstraction and language. I think it all boils down to whether you think reasoning is top-down over all modalities or bottom-up, happening almost in situ, as Jeff Hawkins argues so succinctly.
I mean, in a complex cognitive system like the brain or a working AGI system, I think the answer to is it this way or that way is usually it's both ways, right? And I mean, I think there's top-down dynamics and there's bottom-up dynamics going on. In terms of the role of sensory processing, indeed, it's complex and goes both ways, right? So data comes through sensory processing, and then in cases where sensory processing is too ambiguous, cognitive processing is used for disambiguation. You can have multiple cycles of feedback. On the other hand, for very many people, the process of creative imagination, even about quite abstract topics, can be sensory, right? So like if I think about a Hilbert space or some relatively abstract mathematical construction, like I'm not really picturing the infinite dimensions of a Hilbert space in my mind's eye in a direct way, but there's some at least topological, if not geometric, image in my mind there, right? So clearly, my brain must be projecting stuff from cognitive cortex into visual cortex, and using using matrices and rotations and like sensory knowledge manipulations as a crutch to help it sort through some other type of complex cognitive reasoning it's doing about Hilbert space, right? So I mean, because the brain evolution cobbles together what it can from the resources available, right? So as the human brain was evolving abstract cognition, all this sensory capability was there. So it made a lot of sense to project when it can abstract math into that visual domain, and any type of abstract reasoning. If you could make it visual or auditory, then do it, right? And that, I mean, I'm fairly highly synesthetic, so I tend to see music in concrete visual forms, and so I think you have that sort of leakage, and you have leakage between cognition and vision, and all these feedbacks are important, and we don't understand them well. Like there's an amazing book from, it might have been the 1950s or 40s, by Jacques Hardemer, The Psychology of Invention in the Mathematical Field. He interviews like a dozen great mathematicians as to how they think creatively. Some of them are visual. George Polya, as I recall, said he thought using grunts and groans, like which is also like vector data, right? I mean, that's sounds with complex waveforms to them. When I mentioned this to my oldest daughter, she said she thinks in terms of like typographic words that she can visualize in her mind, which I said, like, how the hell do you think at all? That's ridiculous. But, so that we definitely reuse sensory knowledge within the cognitive domain and vice versa. And you need a tight coupling there, which brings us back to cognitive synergy. You can't say in principle it has to be that way, but that's how the human mind appears to do it.
Though that brings me also back a little bit to, and it's going to be maybe a bit of a repeat, but all of this, the brain being this, highly dynamical, nonlinear, whatnot, and clearly the brain itself is in the domain of, let's say, continuous variables, much more than discrete variables, right? And so the communication in the brain also happens in form of maybe attractors of continuous variables, but nonetheless continuous variables. So is your advocacy for graphs? I'm just sort of a bit, allow me to be a bit skeptical here about, are graphs the correct thing?
At the current time, we're all building AI systems on digital computers, which bottom out on long arrays of zeros and ones, right? And I mean, early in my career, I thought about, like, can you grow a brain in a test tube, or get some like complex nonlinear dynamical chemical soup and coax the emergence of intelligence out of it? Very cool. The world didn't go that way, right? So I mean, we're all looking at series of bits and then organizing them into higher level data structures that obey certain algebras, right? And I mean, they may be linear algebras, they may be float or short float in your programming language. But I mean, I think you could go a philosophical direction, as say Hava Siegelman is an AI researcher who's going in a philosophical direction, saying the human brain uses all the bits in the real numbers in classical physics or something, right? And then, I mean, then it's an infinite algorithmic information thing, and you can't do it in a digital computer. But if or people think, quantum mechanics is used in some profound and fundamental way for cognition. If we set those aside for the moment, those are interesting topics of conversation, but would take the whole podcast. If we assume, for at least sake of concrete discussion, we could build a human-level general intelligence in a digital computer, which I think, I'm not 100% sure, but I think is the most likely case, right? I mean, then, yeah, I don't think that continuous versus discrete is the most interesting way to look at it. I more look at it in terms of what are the algebraic operations that are efficiently supported. And when we look at a knowledge metagraph or a knowledge hypergraph, like we're working with in the OpenCog system, then we have to ask, what operations does this need to efficiently support? And this gets into a lot of nitty-gritty stuff that I'm thinking about a lot now in building Hyperon, which is the new version of the OpenCog system that we're deep into the detailed design phase for. Because most graph databases out there today, like in Neo4j or Kraken, they're optimized to support traversal queries, basically, where you're looking at path from one thing to another. And the way we're using a graph in OpenCog, it's more like the way a graph is used inside a Haskell interpreter or another functional programming interpreter, although our type system is much more flexible than Haskell's, because we're doing gradual dependent typing. And what that means is you're wanting to support a wide variety of flexible pattern matching queries. And so this gets sort of deep into the computer science of it. But what we've done is to formulate a bunch of different cognitive algorithms, including probabilistic logic reasoning engine, evolutionary learning engine, some algorithms for attention allocation and refining motivations, and express these algorithms in a way that the routine operations underlying them boil down to a few common operations, such as pattern matching against graphs or hypergraphs. And this can be fancy pattern matching. Like you may need to be able to match a pattern where a variable is matched by a whole subgraph or something, right? So fancy pattern matching, and then what you call fold operations, like catamorphisms, anamorphisms, and other fold operations, which are familiar to functional programmers. So basically, if you can fold fairly flexible pattern matching over a hypergraph or a metagraph, then we think you can get efficient implementations of all these different algorithms we've been looking at, which represent learning approaches that fit naturally with different sorts of memory, like declarative knowledge or episodic knowledge, procedural knowledge. And for sensory knowledge, Alexei Potapov, who's one of my lead collaborators within our Singularity and Hyperon projects. I mean, Alexei Potapov did a bunch of work connecting the current version of OpenCog, pre-Hyperon, with neural models in Torch for vision and language processing, where you're sort of doing symbolic reasoning on graph nodes that represent layers or other portions of the neural net. And so I think I'm not actually trying to do everything inside the graph. I mean, you could, but on the other hand, Torch and TensorFlow and these things are really, really efficient. So, right, what we liked about Torch is you have complete transparency into the compute graph, so you can represent the aspects of the Torch compute graph inside the OpenCog knowledge graph. And when you compose layers in Torch, you're composing the corresponding nodes in the knowledge graph and so forth. So I don't think the graph has to do everything. But I mean, it happens. We boiled down a lot of human-like cognition into folded and unfolded pattern matching operations on typed metagraphs, and that's kind of wonky to dig into. But on the other hand, the construction of a jet engine is kind of wonky to dig into also.
Yeah, my question was more with regard to. I agree. Like you can implement it, however you want. Ultimately, what you want is the operations on the data. And when I hear graph, I immediately think of exponential blow up in connections. Because if I think of knowledge, it's like, okay, in how many ways can this object be related to that object? And those are just two objects, right? So how do you sort of overcome I have to traverse all these connections. I have to pattern match. It seems like exponential
Wang
blow up.
was a good friend of mine with his own AI project called NARS, Non-Axiomatic Reasoning System. Pei Wang always had one of his many wise aphorisms about AI was that forgetting is just as important as learning, right? And but the other aphorism of his I like even better is when in circular reasoning, when your circle gets big enough, that's called coherence, right? So he, but I think forgetting is extremely important. Your knowledge graph cannot contain everything, of course. But I mean, if you want neural nets to do cognition, you're making recurrent neural nets anyway. I mean, you're having a graph anyway, and then you've got to say like, okay, this is not a completely connected recurrent network; it's a sparsely connected neural network. And why do we have only some of these connections and not others? So I guess I don't think that cutting through combinatorial explosion by architecting once and for all a hierarchical breakdown of your knowledge is a tractable solution. You can do that in vision because the stuff coming in through the retina or the camera, I mean, it does have a very natural hierarchical representation based on like larger and smaller regions in the input field, and even then it doesn't completely work, but it sort of goes somewhere, right? So I mean, this just comes down to you need an intelligent system, right? I mean, you're not making a completely connected graph. You're keeping those links that were found meaningful by the system in some context, and you're pruning those links that are predicted not to be useful in the future. And I mean, the brain, of course, is also a richly cross connected graph, and some connections are potentiated and some are not. And in the epigenetic phase, some connections grow and some do not. It's a very interesting question whether an analog computer, like a continuous variable system, would be much better for implementing human-like general intelligence. It's kind of shitty that the whole field of analog computing dwindled many decades ago. But I mean, in the end, we're all being pragmatists and working with the systems we have at hand.
Well, it is kind of an interesting question. It always makes me think of, Penrose's The Emperor's New Mind, and is there something in the continuity or evolution of the brain that makes it able to do something approaching hypercomputation? Who knows?
Well, yeah, I mean, Penrose's argument, in a way, is kind of silly to anyone with a deep technical knowledge of physics. But if you take it as a proxy for a class of arguments that might include some more sensible ones, it could be interesting, right? So Penrose is making two chief hypotheses, neither of which I think is right, but they might point in interesting directions. I don't know. I mean, the first one is that, like, when he conceives something that's mathematically creative, he's carrying out a non-computable operation of like magical transferring human intuition. And to me, it's just crazy that he thinks he could know that. Like, we don't know what's going on in our unconscious processing. Sure, it feels like divine inspiration, but how do you know it's not just some neural process that's opaque to your deliberative introspection, right? I mean, it could be the case, but how could he know that? The other hypothesis he's making is that this trans-Turing burst of profound human creativity is coming from trans-Turing computing enabled by quantum gravity in microtubules in the brain. And what's amusing is his own theory of unified physics, a twistor theory, is a completely discrete theory, right? So, I mean, there's just no evidence in actual physics of these trans-Turing oracles doing something. So it's, on the other hand, my friend James Tagg claims to have a Penrose-inspired quantum gravity supercomputer sitting on his desk in San Diego. I've not been down there to check it out yet, so I'm not endorsing it.
Well,
I guess, you know, I'm open to the possibility that there is some trans-Turing cosmic inspiration aspect to human cognition. Maybe there is. There's a lot of the universe we don't understand at all. If you're going to go there, I'm also open to the possibility that a digital computer program running on a digital computer could access this source of trans-Turing, like, cosmic wizardry, right? Like, if the gods are implanting creative inspiration into my brain, why can't they plant it into an open cog system?
right, like some gamma rays hit it in just the right way.
Why go this far out and not even further out? And it's all kind of interesting. But if you're trying to be a scientist rather than a philosopher, there's no evidence for any of that, right? And that's seems to me that, you know, that the idea that Penrose has professed that Gödel's theorem limits digital computers from creativity because the digital computer will always have to obey the axiom system it was given, and the human brain somehow bypasses that. I think that makes no sense for a number of reasons, one of which is humans are wildly inconsistent. So, right, I mean, Gödel's second incompleteness theorem is like you can't be reasonably powerful, consistent, and complete. But for better or worse, we bypass that by being like wildly, logically inconsistent, dynamical systems in the first place, right? But the other thing is your digital computer systems are not sitting in a vat. Like they're engaged in practice with the outside world, which is largely incomprehensible to us, and presumably has massively greater algorithmic information than any of us. So you have to look at both humans and digital computers as somehow modulating the self-organizing complexity of the world they're interacting with, right? It's not like they're restricted to their own algorithmic information forever because they're locked in a box, right? So I think it's a lot of fun stuff to think about, and it is. You know, I think that's a difference between my generation of AI researchers and most of the people in the coming into the field now. Is in my generation and the generations before even more so, if you found your way to AGI, you usually found it from a position of trying to profoundly think through, like, what is a mind? How does the mind work? How the hell should we approach this whole thing? And you had to go down to ground zero and try to understand what is thinking. And maybe you got absorbed in that rabbit hole forever, or maybe you came out with some tentative hypothesis and decided you want to implement something and explore some concrete class of ideas. Now it seems like people come into the field and they want to do AGI because their mom told them it was a good way to make a high salary or something, right? And and of course they assume Google has already figured out how to do it, so it's just a matter of putting in a few details to some of the algorithms. So it is a remarkable change in sort of the orientation of the average person going into the field. Of course, humanity is diverse, and there's all sorts of complex, crazy young people too on the edges.
Yeah, doing a PhD now is the extended interview process for Fang. But anyway, I wanted to get on to AIXI. So you've said that Hutter's universal AI theory, AIXI, the main article of faith at DeepMind, by the way, serves as a credible, although debatable theoretic approach to AGI, and that several proto-AGI systems are emerging from it already. I'm not sure which ones you meant, but we'll get to that in a sec. But your core belief here is that intelligence is closely tied to the creation of procedures that achieve goals in environments in the simplest possible way. You seem to believe that the best way to think about AI is in terms of a discrete decision-making agent. Now, we think that AIXI is a kind of tautology, and the recent DeepMind paper, Reward is Enough, is also full of tautologies.
I mean, all mathematics is a tautology.
That may well be the case. But for example, if it were possible to find an optimal agent, you might need to have an AGI already. But anyway, AIXI also assumes that the environment is computable. And I think there's a huge gap between some of the very theoretical notions we talk about in AGI and reality. AGI researchers cite apparently incontrovertible and mathematically rigorous articles of faith, whether it's AIXI, universal function approximation, or the so-called Turing completeness of neural networks. They're not Turing complete, by the way, folks. Francois Chollet similarly presented a measure of intelligence formalism, which also wasn't computable. Now, you've said that you think human intelligence is subsumed by the AIXI agent, but I'm interested to know whether you think that AIXI is a specialized form of intelligence or a general form of intelligence. After all, it's just a static computer program, right? How could it possibly be generalizable?
Well, the main limitation of AIXI, apart from it needing infinite computing power to do anything, the main limitation of AIXI is it's not an open-ended intelligence in the sense of David Weinbaum. It's a system that you give a reward function, right? So if you're willing to narrow to that context, to say that I'm going to consider an intelligence as something that's maximizing expected reward of a given reward function, I mean, then the theorems of Marcus Hutter show that AIXI can do that, and it can do that within a constant factor. It can do that as well as any other system could optimize that reward function in that environment, right? So that in that, but it reminds me of a story every mathematics grad student in my generation learned. Is like a physicist was brought in by a farmer to figure out how many cows could fit in their pasture. The physicist starts out, okay, assume a spherical cow, and then goes from there. The farmer kicks him out because cows are not spheres, right? Then they'll just all roll down the hill. But I mean, within the physicist paradigm, that's where you start. And so, I mean, XE is definitely assuming a spherical cow, right? And you run into limitations that way, but it still tells you something. To me, it's interesting to know that if your goal is to optimize expected reward in a computable environment, and resources are no issue, then AGI is trivial. I mean, AXE does it basically by, at each step of operation, it searches the space of all computing programs to figure out which one would have given it the best answer in the past. It executes that program to generate the next action. So what that teaches me, I mean, it's nice math. As a mathematician, I find it a satisfying bit of theory, but I mean, Newton's, classical mechanics is also a satisfying bit of theory, and it doesn't fully describe the world. It has limitations, right? So what that tells me, though, is that even within the constraint of expected reward maximization, which is a limiting way to look at general intelligence, it's all about limited resources. And this goes back to Pei Wang, whose definition of intelligence is adaptation to the environment given limited resources, which I think that in itself doesn't quite capture everything I care about with general intelligence, but I think it's pointing in a good direction in that, you can optimize the reward function just by brute force enumeration of all possible ways to do things, and then Bayesian reasoning on that. Human brain doesn't do that. Why doesn't the human brain do that? Because it evolved with limited energetic resources, right? Well, and this tells us something about how to think about being practical, building practical AGI systems. I mean, it tells us we need to think about, what are the resource constraints and how are we dealing with them? Now, I mean, in a sense, that's obvious anyway. In logic, everyone knew pruning the search tree is what really matters. But I think the limitation of maximizing expected reward, though, is also a quite serious one. Like, there is no loss function that those of us in this call are systematically maximizing throughout our lives, right? I mean, that's not what humans are doing. If you look in Weaver's thesis on open-ended intelligence, he's looking at it a different way. He's looking at it like an intelligent system is simultaneously trying to individuate itself, meaning to keep its own boundaries there and keep on existing, and it's trying to transcend itself in what he calls a transductive chain, like to build something new and better out of itself. And this is like being and becoming, back to Hegel, right? And I mean, there's a contradiction between these two, which leads you in a paraconsistent logic direction. But if you look at our goal as to maintain ourselves while transcending and improving and developing ourselves, it's not clear this sort of open-ended intelligence motivational system is well captured by writing down a loss function or an expected reward function and saying you're maximizing that. Like I'm sure the reward functions that I approximate have changed over the course of my life so far, and I'm only 54 and I'm still in human form, right? So I think that's a fascinating body of theory, but of course there's many limitations.
Could I just say that, because you're anthropomorphizing a little bit there, but just looking at the mechanics of because I'm really trying to understand this reward function. It has to be a function of the environment, but where does it come from?
Yeah.
Why isn't it deceptive? Why is it a smart idea to pluck a reward function out of thin air and optimize on it and then say?
Well, it probably isn't, but Marcus Herder didn't make that up, right? I mean, he's just putting statistical decision theory together with algorithmic information theory. I mean, if you want to be cynical, you could look at AXE as the sort of a reductio ad absurdum of reinforcement learning, right? I mean, he's just extrapolating to the logical consequence of it, like this will do it, and then you're done.
But
right?
Go on.
So, the DeepMind paper, I don't know if you have read it, but this paper about reward is enough. It makes a slightly different claim.
That's a profoundly silly paper. Although I mean, I love Rich Sutton, and I mean he's both a sweet, good-hearted, wonderful human being, and he's contributed fantastic things to the field. But I think that there's a long pathology in the AI field, which is assuming that if some algorithm or approach in theory is enough to lead to human level AGI, like given enough resources, that matters a whole lot. And I mean, I think, Schmid-Huber's Gödel machine paper shows that logical theorem proving is enough, but it's pretty easy to see that genetic programming must be enough. I mean, if you have a big enough population, you're evolving programs. And so, I mean, in the end, I would say almost any learning approach will be enough if it has the property that no operating program for the AI system has probability 0. Like as long as you will explore the search space of things to do without leaving out any options, in the end you'll get there.
Even monkeys are enough.
It's not that RL is enough is wrong if you construe it broadly enough. It's just not. It's not interesting because I don't think it's enough in real life, given realistic resource constraints. Just as I don't think pure logical theorem proving is enough in real life, given real resource constraints.
So I just want to push back on that a tiny bit. So there was a chap called Francois Chollet came along, and he wrote this beautiful paper on the measure of intelligence. And
I know Francois.
We love Francois. He's our.
I think he's giving a keynote at our AGI conference in October.
Oh, brilliant! We've had him on the show, and we're his number one fans, actually. But no, anyway,
he's awesome,
he came along and he said, because obviously another conception of intelligence is about flexibility, and he says that intelligence is about the ability to adapt to novelty using knowledge you already have as efficiently as possible. And essentially it's about being able to create a skill program. But in his formalism of intelligence,
I mean, that's basically the same as Pei Wang's adapting to the environment.
Well, not quite. Not
given
quite.
Limited resources.
The difference is, and I expected. I hope you'll be kind of you'll be into this idea that our measure of intelligence should take into account experience and priors and knowledge, because we're knowledge people, right? And that doesn't seem to be happening with some of these conceptions of intelligence, because otherwise, surely you could just brute force. You could just do every possible thing in the universe.
I mean, you can do AXA using relative algorithmic information relative to some assumed knowledge base. So that doesn't change any, literally changes almost none of the math. I mean, that's so that wasn't Marcus's focus. The thing is, with all his theorems, they're all kind of in the limit anyway. So I mean, if you assume some finite body of knowledge, it just changes the multiplier constant by some fixed amount and doesn't matter. But yeah, the contextual aspect of intelligence and the fact that it depends on what knowledge you're bringing in obviously is incredibly important in actual reality. And I mean, what we care about is human-like general intelligence in human-like everyday context, which is what that's what we care about. We care about initially. So I do think that's important. And of course, part of these contexts is that you need to be able to get out of the way of the car before it runs you over, right? I mean, you need there's temporal and spatial and energetic constraints on the system, which are coupled in particular ways with the task set, right? So that there's a lot of subtlety there. I mean, I think Francois Chollet's conception of general intelligence, to me, is very similar to Pei Wang's, which is weaker than Weaver's, because it's sort of, to me, that conception of adapting to the environment based on limited resources, even if the environment is unpredictable, and extrapolating from the past to adapt to the environment, that captures the individuation part of Weaver's notion of open-ended intelligence. It doesn't capture the self-transcendence part, where an intelligence is trying to develop into something fundamentally beyond what it was. And I think in psychology, there's a difference between learning and development, right? And development kind of fundamentally refactors what the system is. It's not just learning to do stuff within the architecture of the system. And I mean, I have at home here, I have a 3-year-old kid and a 5-month-old baby who are my fourth and fifth human offspring, right? And at these ages, it's not just learning, right? I mean, they're new portions of their brain are coming online, and or new networks or assemblies in their brain are coming online anyway. And the way they come online is conditioned by their environment and by what they're doing. And I would want to embrace fundamental development of that nature as a key aspect of general intelligence. I mean, you might say we're just not ready to deal with that yet, and we want to master learning within a given stage of development first. But it's a little subtle if you look at the human analogy, right? Because humans, as they grow up, they're radically developing in conjunction with the learning that they're doing, and the fact that our one reference system is doing development and learning concurrently in a coupled way would suggest that may be something we should take into account. And that if you go computer sciencey and look at logic systems and program learning, that brings you toward like meta reflection and if you have a programming language with a type system, can the system create new types and insert them into its interpreter or something, right? I mean, the form that fundamental development and the system refactoring itself takes in the human brain versus in a more computer science-based system like OpenCog, Hyperon, may be different. But still, I think focusing on the development aspect pushes you in a different direction, which I don't see even the more radical voices in the current deep learning world, like Francois Chollet. I don't see them going there yet, but maybe in a couple of years. Things are evolving fast.
Could I ask you a quick follow-up on the notion of pure intelligence? So I know you subscribe to Ray Kurzweil's view of the singularity happening within the next few decades. And personally, I subscribe to Melanie Mitchell and Francois Chollet and Douglas Hofstadter. I know you said that he was a huge inspiration for you. Their school of thought is that there's no such thing as pure intelligence. It's better thought of as a process, through embodiment, etc. Our intelligence is surprisingly specialized, even though we can write software to solve problems which we can't. So how universal is intelligence? And in particular, how anthropocentric is intelligence? Now, you said on Lex's show that there are many ways to build a flying craft, right? Perhaps the same is true of general intelligence, but it's also fascinating how many emergent features of intelligence may be decoupled in some sense to the intelligence which produced it. For example, different intelligences might discover the same mathematical axioms. It's almost as if all roads might lead to Rome. So how do you think different intelligences might be comparable?
Well, I think all the roads that we're talking about leading to Rome are existing mostly within the same physical universe and even on the surface of the same planet, right? So there's a lot of common context there. And I would say if you want to accept known physics as an axiom, it would follow from any conception of intelligence I know of, it would follow that no finite physical system is ever going to be maximally and wholly general intelligent. I mean, there's the like Beaconstein bound for the amount of information that can be stored in a certain amount of mass energy. Like you're going to have finite algorithmic information for any finite physical system. You can't build AXE or like a full on Gödel machine in the physical universe. And yeah, that means you're not creating a maximally general intelligence. And as I've often said, humans are not a maximally general intelligence. I can run a maze in 2 dimensions better than 750 dimensions and so forth, right? And I mean, humans, I was a math professor for a while. I saw how even fairly intelligent humans struggle with very basic mathematics. Like people. I mean, we elected Donald Trump president. We can't be that generally intelligent, right? People have profound limitations in their general intelligence, but yet that doesn't mean everything should be considered equal. Like I still think it's meaningful to say, like, I'm more generally intelligent than this glass or than an earthworm or a dog or something. And so I guess maximal general intelligence is. I can't say it's impossible to exist. I can say if we assume the laws of physics as a context, it doesn't exist in that domain. Like there's an alternate phenomenological view where the laws of physics are built up by the perceiving mind itself. If you want to go the Buddhist psychology direction, maybe everything begins from a ground of infinite general intelligence. But once we get trapped in this samsaric realm of the physical universe, and we're down to finite algorithmic information, right? And so that's fine. There's still a lot of room to go way, way smarter than the human brain without hitting the Beaconstein bound and the limitations of general intelligence posed by the laws of physics. Like, just like we're not the highest jumpers or the fastest runners, we're almost surely not the smartest thinkers, right? So you can get through a singularity and probably a whole bunch of multilarities beyond human level general intelligence before you hit the limitations imposed by the laws of physics. And what the laws of physics will look like to the beings we created that are 100 times smarter than us, who knows? We seem to have revised the laws of physics radically every 50 years or so anyway, right? So yeah, Douglas Hofstadter, I mean, he had his book Gödel, Escher, Bach, which I read in the mid-'70s when I was a kid. I mean, that was the first time I encountered sort of that whole academic AI community, just sort of in passing during Gödel, Escher, Bach, because before that I knew AI only from science fiction. So it was just very inspirational to me to see how these like actual professors and serious thinkers were thinking about how to really build AI systems. But I've diverged from Douglas in various ways since then. I mean, he thinks the singularity is kind of a bunch of bunk, but he also thinks current deep neural systems are completely unrelated to general intelligence, and there's almost nothing to be learned from them except what not to do. And I don't want to misquote Douglas, who has his own nuanced point of view, but that's the impression I get from conversations with him on this anyway. Whereas my view is more that these currently highly successful deep neural models and other ML approaches are quite informative about how to emulate parts and aspects of human level general intelligence, and they're great for building some kinds of commercial systems. I think they're missing a lot of aspects of human like general intelligence, and that incrementally improving on them probably is not going to be the most effective path to get to human level general intelligence. But I don't think they're totally off in a useless direction. There's all sorts of cool things to learn from there. And as you know, unlike Douglas Hofstadter, I am an optimist that we're going to get to general intelligence beyond the human level during, for example, my career, assuming nothing very unfortunate befalls me. And this will bring about some form of technological singularity, which is a whole other big topic. But yeah, while we're on the phrase singularity, we should at least briefly mention SingularityNet, which is a project I'm leading at this time also.
Yes, we were also pretty interested in SingularityNet. You said, if I recall that correctly, that OpenCog and your rewrite of it, they're sort of about connecting knowledge in a quite integrated sense, narrowly, maybe even in RAM on a single computer. And then SingularityNet is about connecting knowledge in a loosely coupled way across essentially the entire internet. So in essence, SingularityNet is, if I understand correctly, a marketplace for APIs, right? It's not much to do with AI per se. Like I can put up an API that, gives me database access and like, why do I have to pay for it and all that kind of stuff. Could you elaborate a bit?
Sure.
Why is this a good substrate from
an AI theory view? I guess you could view there as being multiple ways to get to a practical AGI. And one way would be you build, some group builds a really smart algorithm that is just running on their computers the way they want it to, and it's thinking and learning and abstracting. I mean, it may get out of control eventually, but anyway, it's initially behaving by one group's design. Another approach, which is interesting in concept anyway, is you have a more decentralized network where different parties have put different AIs doing different things. One guy may have put a perception engine online for visual data. Another guy may have put an abductive reasoning engine online. Another guy put a computational creativity engine online. These different components have a language for describing what they can do to each other, for describing their properties to each other, and then general intelligence emerges or crystallizes from this network of agents, and no one human party designed it. Right now, some folks have hypothesized this would just happen on the internet, right? So just the internet is a playground where multiple parties are putting AI systems out there, and they're all communicating and combining and connecting with each other. If you think about it more deeply, it seems like the way the internet is constructed, it's not very well oriented toward this sort of autonomous assembly of algorithms written by different people into autonomously acting super assemblies and so forth. But you could build a system that was, right? So what we did in SingularityNet, we built a system that could serve as a sort of primordial soup of agents, where anyone could put an AI agent into the SingularityNet framework, and the AIs in the system can describe to each other what they do, what data they take, what outputs they give, how much processing power they take to do a certain thing, how much they're going to charge. So there's a language for the AIs to describe what they're doing to each other, and then the way blockchain is used there is just in the plumbing to ensure that there's no need for a central hub in this network. Like anyone can put an AI online to this network. It announces it's there peer to peer to the other AIs in the network, and then it's part of the club. And some folks within our SingularityNet group, they're really pushing to have benevolent human level AGI emerge from this sort of society of minds where different members of this society are coded by different people with different aims in mind. The way, I mean, if that happened, I would be the very proud father of the emergent network in the singularity of the emergent mind in the SingularityNet network. It would be awesome. But I mean, the way I'm looking at it is more like I'm building OpenCog Hyperon, which is a pretty specific cognitive architecture. Part of the reason we're moving from the legacy OpenCog system to the Hyperon system is I want something that better makes use of large-scale, massively distributed processing power. The other main reason is I want something that interfaces more efficiently with deep neural net libraries. But part of the way Hyperon will do massively distributed processing is through integration with SingularityNet platform. So the way I'm looking at it is we can roll out OpenCog Hyperon on the SingularityNet network as a bunch of interacting agents. And this can be really, really loosely, I mean, this can be like the cognitive cortex of an AGI that lives in SingularityNet. So maybe somebody else writes the visual perception cortex, and we've written the cognitive cortex with Hyperon, and then someone else writes, a cerebellum that controls factory machinery. Someone else writes a cerebellum that controls humanoid robots, right? And the really interesting thing would be if the visual cortex, so to speak, that one guy wrote, and the Hyperon-based cognitive cortex that we wrote, if they could interact in a way that enabled like substantive feedback between perception and cognition, like can they share intermediate state along a channel that they created? And so together with IOHK, the company that works on the Cardano blockchain, we're working on what we're calling an AI DSL, which is a very rich sort of dependently typed functional language for communication between different AI processes in this network. So I mean that's the vision and aspiration with SingularityNet. And I would say within our organization we have some people who think Hyperon is just one AI system among many that will run in the decentralizing like prebiotic soup of AI that will self-organize into intelligence. We have others who think Hyperon is going to be the AGI, and then the fact that it's deployed in SingularityNet, it's nice that it will be there instead of AWS. It may stop governments from taking it over once it becomes a super intelligence, but they think it may not be critical to the actual AI part of it. And I'll be happy if it's either way or some combination of those.
I have a question though about I mean, I assume at some point the publishing of APIs, the discovery of APIs, that has to be automated. The machines have to be able to do that themselves. And I mean,
yeah, it has to be automated.
But so far nobody's been able to successfully do that in any API context, even outside of APIs. It's like a notoriously difficult problem, right? So how do we get away from the sort of still human bottleneck, the need for humans to sit there and write down APIs and write glue layers and understand the semantics, etc.?
Yeah, I mean that's a quite hard problem, and I mean I think that to me is a problem where automated reasoning meets functional programming. And the answer may be found there. And we've seen this, and this is the solution to this is totally not completed and deployed in the current SingularityNet platform. Like right now, humans are writing the APIs, so we're totally not there yet. But if the AI agent is written in say Haskell or another higher level functional programming language, I mean, then you have a lot more affordances there for the same reason that you can do automatic verification of programs in these languages much more easily than say a C++ program. And we deal with questions there like, suppose someone wrote, an algorithm doing decision tree learning or something simple. Like, suppose you want that algorithm to operate in a secure multi-party computing context with security for sharing data in multiple places. Or you suppose you want that algorithm to run distributed across a bunch of machines. Can you do automated program transformation of the AI algorithm to allow it to do that without a human having to rewrite it? And what you clearly, the route I see to making that possible is where the algorithm is written in Haskell or OCaml or some higher order some functional language, and you have a semantic description of what the algorithm does, which is linked into the actual code, right? And I mean, until you have that, you're kind of flailing around. And I mean, I think if you have those things right now, we could do that sort of thing in an academic playground sort of sense. Like we could do it with sorting algorithms and simple list processing algorithms and stuff, but it's not tractable to do it with really, really complex algorithms. But I think there's an interesting path there. And this is one of the reasons I'm so psyched about the partnership of SingularityNet with IOHK and Cardano, because they've got an army of brilliant functional programming academics within their organization. And here we're going away from modeling the human brain, and we're going into, okay, we're taking cognitive architectures that are loosely inspired by the human mind, but then we're sort of we're doubling down on current computing infrastructure, right? And we're saying, okay,
yeah,
let's deal with programming languages. Let's make a codic modality where the AI can sense programming languages. Let's make a cerebellum where the AI can manipulate the execution graphs underlying a Haskell program, and just embrace that. And that may be the right path to like a meta-reflective AGI system. But there's interesting balance there, right? Because the further you go in that direction, the less you can draw on human cognitive science, let alone neuroscience, to motivate what you're doing. But it's very, very fun domain to be playing with, at any rate.
Just a quick question, because it sounds like you're, in a way, describing the ultimate microservices architecture. But sometimes it's more efficient to move the compute to where the data is and to do things monolithically, end to end, right? Because you just have so many I/O bottlenecks and these network effects.
Yeah, it can be. With SingularityNet, it's not like all the processing has to be on everyone's phone or in their like pacemaker or something, right? I mean, you can have a server farm running a whole bunch of nodes. The question is really, if you want to move those things off that server farm, like what are you doing? Is this just a bunch of nodes in a decentralized architecture who happen to have gathered together on that server farm because it's more efficient for them to have a conversation that way? Or does moving them off that server farm involve, doing a lot of human work to port from the APIs of that server farm to the APIs of something else? Because right now we run a lot of SingularityNet agents on AWS, but the SingularityNet daemon wraps up all the AWS specific calls, so that the agents can be moved off AWS without changing any of their code. But yeah, the data that's in buckets on AWS will be accessed much more slowly by them once you move them somewhere else, but they'll still be accessed by the same API calls.
Awesome. Dr. Ben Goertzel, it's been an absolute honor to have you on the show. Thank you so much. We really appreciate you coming on.
Absolutely.
Yeah,
thank you.
Thanks for
Very
having me.
interesting.
This is
Thank you.
all fascinating stuff, and similar to with Lex Friedman, it's good to be able to dig a little deeper than in the average podcast.
Absolutely. Well, yeah, we pride ourselves on being a technical podcast. So yeah, we really appreciate
It's a good
you doing
show.
that.
Yeah.
Amazing.
It's a good
Amazing.
one.
Thank you so much. So that was Dr. Ben Goertzel. How did you guys feel about that conversation?
I learned a lot. I found a lot of what he had to say super fascinating, and gave some great references to follow up on. So I've got some fun reading to do when I can make the time.
What was your comment, Keith? He said that the AIXI was the reductio ad absurdum of intelligence or something.
No, of reinforcement learning.
Right.
There are a bunch of great quotes in there. And then I think he said Pei Wang, or I have some note here on who said this, but I like as the circle of your circular logic becomes large enough, it becomes a coherent system, something like that.
Dr. Kilcher, what did you make of the conversation?
I say this almost every time, but I think it highlights the importance of just talking to people and because we were reading all of his papers, watching his talks and so on. Ultimately, when you interface with someone one-to-one and really give them a chance to directly respond to questions and so on, people always seem to be like a lot more agreeing, and you think a lot more like, oh yes, that's actually true. People seem a lot more, not that he was ever unreasonable, but people seem in your mind a lot more reasonable than when you just read their papers and you go like, what?
Yeah. I guess that's a reason for building Sophia, right? To give that human interface with.
Yeah.
Well, I have to say, he for being kind of out of the mainstream of AI, he's very good at marketing in general, right? Generally, the things he does, be it this with SingularityNet, Sophia, and so on, even or even OpenCog in a sense, they seem to be well received, and people seem to pay attention. And if it is only because Sophia has a human face, which everyone in the technical field knows, it doesn't matter if an AI has a human face, right? And there's a bit of this emotion thing like they have in that project. But now Sophia, every time a journalist wants a picture of an AI, they put Sophia there, right? So it would have been also interesting to ask him maybe a bit about a few tips, because that is a thing he's definitely successful at, right? Being sort of businessy while doing his own thing, while not being in the mainstream, right? Not following the hype, which I find really cool.
Yeah, he is an enigma to me. He's such a unique character. He's a rare breed. But reading his papers, at first I was thinking, my God, there's so much technical jargon in here. And I don't think it was gratuitous. We had this conversation. At first, you almost don't want to believe it. You think, oh my God, I can't understand what the hell is going on here. But you go and look up all of these definitions, whether it's distinction metagraphs or heterarchy or, Galois connections or whatever else. And it's all completely legit. The only answer is that this guy is a polymath. He is incredible. Because I went online, I saw, is there any criticism of this guy? And there isn't. So... Yep. But at the same time, he is a businessman, and he is making the case, and he is getting lots of funding successfully. He really is spinning all of these plates at the same time, and that's pretty impressive.
Yeah, I agree with you. I think it seems clear to me that just the magnitude of his knowledge, and also, by the way, pragmatic experience. Though he has this huge background of theoretical knowledge and study, he also has been involved in building systems. And in my opinion, that's a huge benefit to anyone's learning, is actually going out there and trying to practice, trying to build something, trying to do something in reality. He's done that. And so he's just got this huge mountain of knowledge here. And when you ask him a question and we're trying to get to point Z and we're starting at A, there's a long path there. And I'm sure all of us have been in this situation when, say, a younger kid asks you something about, what's string theory? And you're like, okay, we got quite a distance to go from what to string theory. And so it's a long path there. And I think that's what you run into a lot with Ben when he's answering questions.
But he's almost got too much knowledge. It's kind of overwhelming because he's all like, we watched some videos because today we framed the conversation, and I thought the conversation with Lex was really good, again because Lex framed it, because some of the conversations you hear with Ben online, one minute it's Nietzsche, the next minute it's parapsychology, the next minute it's the meaning of the universe, the next, do you know what I mean? And it's all over the place, but the reason it's all over the place is because he can go all over the place quite confidently. But there were a couple of things that I noticed, though, because I kind of got the impression with Ben at the beginning that a little bit like Arai, who we had on the podcast, he almost thinks that AI should just be this confection of everything but the kitchen sink. Let's throw neural networks in there. Let's throw, logic systems in there. Let's do evolutionary programming. Episodic memory, no problem. That's a simulation. Let's just kind of conflate everything together and believe strongly in the emergence of some kind of AI on top of that. And that's where I think we're a little bit more skeptical.
Well, I have some feedback on that, which is he also has a massive amount of knowledge of human cognitive processing, right? And so I think that, in my opinion, I'm guessing that leads him to just have a tremendous amount of understanding of the value in what's already been built by evolution and kind of the human mind, that we need to utilize that if we want to make more rapid progress in AI rather than just rediscovering all this stuff, 500 years from now.
On SingularityNet, Yannick made a video about SingularityNet. I assume that we all agree that something like SingularityNet is a core substrate for any future artificial general intelligence, with all of the caveats that we spoke about. Is it really decentralized? I'm not sure it is. Some things are on the blockchain, but presumably if I want to plug my AI in there, I'm probably going to be a private company, and it's probably going to be surprisingly centralized. And also, is it efficient to have such a strong decoupling between all of the services and having to, the IO of having to send the data between the services? And as you said, Keith, the real problem is it's an intractable problem to describe what a function does. Let's say we plug in Google's face recognition API and Microsoft's one. It's almost impossible to describe the comparative behavior of those two APIs.
Well, especially to have a machine be able to do it, because it has to be automated. When you say to me, "Oh, have you seen Yannick's new facial recognition program?" I pretty much already know what it's doing, right? I know the semantics of that. And maybe I just I can just skim through his FAQ and kind of get the rough idea of like the little nuances or the cool stuff that he's done to make it better, right? That's machines can't do that. Like, they can't do that yet, rather I should say, right? And people have been working on this API, reflection, automated discovery, standardization, etc. for forever, and it's an unsolved problem. That's the real
But even
difficulty.
If they could do it, it would be brittle, right? Because a facial recognition API, you're talking about a neural network with billions of parameters. It's not possible to meaningfully compare those two programs.
Well, yeah, it's not possible. It's more about what Keith, I think, said, is that maybe it's not that we can describe all the programs we have today in terms of an API, right? But tomorrow we're going to come up with a variant, even of a deep learning system, even of a face recognizer, but that does something different, right? The input is still going to be, give me an RGB array, and I'll give you like a list of XY coordinates. However, the meaning of that is it's going to be so hard to describe this in any form of way that other machines could then use as a subroutine. What other machines could then be like, without humans telling them to go face recognize, machines could be like, oh wait, this thing could be useful for my thing, right? And
But look, the whole point of this system is to have a customer interface where you abstract the actual physical API from the customer. So the customer just says, I'm getting facial recognition, but I don't know what the API is. But it's even harder with AI models because you have so many failure modes, right? So if I did switch over to Google's API tomorrow, maybe because the system decided it was cheaper, the failure modes are different. This is such it's just technical debt.
Well, the SingularityNet paper describes that you could have some sort of agents in the system. Some agents would be there sort of to purely evaluate other agents. So technically that problem could be solved in that you could say, I want facial recognition with these and these and these sort of quality specifications, and then other agents would sort of continuously evaluate all the APIs that are offered and could tell you, well, this API is good in this kind of data and this API is good in this kind of right? Once we solve the description problem, these kinds of things become possible, but without it, not so much.
But see but that's the key there, is like, because Yannick said could, right? There's that little word in there, and I noticed this with Ben, which is that, again, that because he's such a vast knowledge base, he's easily flowing from stuff that's already been done and proven to things that are visionary, and occasionally there'll be a little if that's in there, or could, right? And if you don't pay really careful attention to that, you'll miss the fact that we're talking about something hypothetical that hasn't been done yet. So I'm really glad that he was very clear about, in some of those answers in Singularity Net, saying, okay, this isn't there today, right? This is an active area of work. We don't have a solution to this yet. So that we know, like, we're not there yet. And this is going to be the really, really, really difficult part. I think it's been an intractable problem for a long time.
Exactly. And I think another interesting dichotomy is he's kind of like an engineer. He says he can engineer AGI. I'm an engineer as well. And engineering, to me, software engineering is all about immutability, reproducibility, testability, etc. So I want to write some software. I want to write some tests against it. I want to make sure the tests pass, and I want to put it into production. Do I want to put something into production which is dynamically changing and morphing? God, no. I mean, that sounds like a nightmare to me.
Sounds like fun to me.
It's a nightmare of possibility.
No, but even when we design ML DevOps systems or anything like that, we build the model and then we come up with a load of model validation tests and so on, behavioral tests. We decide that this thing's good to go. And then when it's in production, it's immutable. We have versioning and all of the customers are calling that version of the model. We do not change it. I mean, for God's sake, could you imagine if I just changed the model and the customers still thought they were calling version 1?
I mean, we'll have to change maybe a bit of what we expect out of, like, we're not gonna use a Singularity Net in the future for, doing our Excel spreadsheets. Like, all of the things we do today will still be handled largely by, classic software. I think we're going to have new modes of getting serviced by the internet with some of the stuff we want to do, where it is just going to be an acceptable mode of, this is kind of what the network, it's more like if I go to 4chan and ask around to get help with a problem, right? Sometimes I'm going to get a good unexpected answer, better than I could have come up with myself. Sometimes I'm going to get some trolling. Sometimes, it's just going to be different.
This is really interesting, though, because I think that what you just said there, Yannick, that is the mindset of a lot of people in the deep learning community right now. That is the mindset of people who think that we can use GPT-3 in a business setting. And I think we can't, right? Because I want to be able to test things and I want to understand its behavior and understand its inner workings. Whereas another mindset is kind of like, well, let's just sample this thing and, it might work, it might not work. Do you know what I mean?
Sure, but if you don't want to use a product based on GPT-3, then don't use it, right? I mean, that's the question is, would anyone want to use it? Would anyone want to pay for a service that comes from Singularity Net, where you can't exactly be sure what you're getting any particular day? I don't know, but
well, that's interesting, because if you think about it, there are some use cases where it's acceptable. So we all agree creative fiction and art, that's fine. Actually, information retrieval is fine as well. And that's because you have a human operator on the end. And the human operator is kind of interactively interpreting and querying this thing. But anything non-interactive or anything which is safety critical or anything which we need to understand its inner workings, then I think we couldn't use it. Interesting, though.
Sure. Yeah. No. I mean, yeah, of course. But that's the same today. Right? If you program a software and that software, even though it's programmed in a classic method, can't fulfill the safety criterion, we don't use it. I do think it's going to be a new mode of operation where people will understand. Like, as long as people understand what you're getting, it's not like classical software. and they're willing to accept that, then why not?
Well, what about the GPT-3 suicide example?
Well, if people think of this GPT-3 therapist not like a real human therapist or a piece of infallible software, but like, what if I went to 4chan or to Reddit and asked, what should I do? There are going to be some few responses saying, please go away, please leave the earth. Same thing.
Well, yeah, I mean, maybe the problem is just that we anthropomorphize AI too much and we don't have that way of thinking about it.
Or too little, right? If I actually anthropomorphize GPT-3 as a collection of the whole internet, then I'm going to be clear on, hey, the whole internet actually contains people that are not very helpful as well.
Mm-hmm.
Plus, I think part of the idea is too that, if we have this better platform, SingularityNet plus, let's say, OpenCog and whatnot, we'll end up with better AIs, like AIs that won't suggest you go kill yourself, or that sort of flawed AI will be part of a system, and then downstream there's kind of like a sanity checking AI that understands human emotion or something and goes like, I don't think you can say that to this patient, we even have that today, right? Which is like, there's plenty of let's say popular figures on Twitter that people wish had, just an admin that would kind of double check their messages before they go out, right? So I think the idea is we can build better systems, and then of course there's going to be extensive testing, and that's all part of like, okay, this little part of the graph over here, it's really been thoroughly tested for self-driving now for something like the equivalent of 1 million driving hours or something we've done in the last week. Okay, it's ready to go to the first ring of users, and then so on. So all the same engineering paradigms can be applied to this. It's just that only the kind of upfront design work won't be the same.
Yeah, and I think it's really interesting what he's done. As I said, as a software engineer, I'm really, really intrigued by what he's done. And we've been speaking to quite a few symbolists recently, and it kind of feels that he's actually done what they've been selling us on. It's OpenCog. He's come up with all of these different categories of knowledge and ways to represent them, ways to take many different diverse AI algorithms and get them to talk with each other using common representations. That's exactly what they've been talking about doing.
Yeah, but you got to pay careful attention to those little qualifying words in there, like if, could, etc. Some of it's done, some of it's not done.
I think the limiting factor is not whether it can be done or not, it's just whether it will work. And I think he said that the existing system was written some time ago, so there's a computational problem with scalability. As we were asking him, I think scalability is always going to be a problem when you're traversing these graphs. You have an exponential blow up. But the bigger question, though, is to what extent could this kind of emergent, interesting dynamics happen? I can see how it happens in the brain and, in a corporation. But if you have a society of minds where the minds are discriminative AI algorithms, how are those minds going to create a kind of chain reaction and interesting dynamics emerge?
Well, yeah, that's more of a belief, I think. I mean, emergence, to me, it was always kind of a magical term where you just say, well, things come together and emerge. And my question is, I've no doubt that emergence happens, and if you put stuff into systems, especially open-ended systems, then maybe some complex, behavior will emerge. Though why, like, the transition from something will emerge to AI will emerge, that is my kind of main contention with the whole, with the people that just kind of say, okay, things, and then say emergence, right? Like, give me a tangible reason why the thing that emerges should be intelligent. Because, in, like, you look at ecology or so, and lots of systems emerge, right? And sure, you can call like an ant colony intelligent, maybe, right? maybe you can make the argument, but even absent ant colonies, most ecological systems aren't by any of these definitions intelligent, yet they're incredibly complex, right? They emerge out of the behavior of, so why emergence, to me, it doesn't mean intelligence will emerge. Like something will emerge doesn't mean intelligence will emerge. So I need an additional reason there.
I think that's a philosophical cul-de-sac, right? I think that our planet is an intelligent agent. James Lovelock Gaia theory, he kind of says that you can think of all of the ecosystems on the planet as being a kind of intelligence. So whether it's an intelligence or not, I think we could debate that. But it is a complex dynamic system. And maybe you could think quite generally, as Kenneth Stanley does, that intelligence is a kind of information accumulation, right? But I think the problem is brittleness, because when the primitives because he has this kind of type theory system of how the agents talk to each other, and it's so specific. The reason why you get emergence in the brain is because there's no brittleness. It's very, very easy for the neurons to communicate with each other, and it's very, very composable. But when your modules expect a very specific type of contract with a very specific type, it just seems to make it less likely that you'll get complex behavior emerging.
Over actually really through the process of the show, like say talking to people like Friston, the free energy principle, and others since then, in answer to kind of Yannick's question, I think that intelligence emerges almost necessarily from any environment in which uncertain processes threaten to eliminate your code. So in other words, in order for an intelligent thing to survive and replicate itself, it has to have some measure of ability to predict the future, and to predict the future in a flexible way. Otherwise, all this stuff that keeps bombarding it, for us, it's physical stuff. Okay. In the case of Singularity.net, it's a marketplace of demand. So varying demands are bombarding the market, right? And there's this cryptocurrency economy in there. And so if you don't accumulate enough wealth to do your processing and survive, then you'll get fewer ratings, and eventually you'll disappear, or you'll be in a dead node, a dead zone of the marketplace, right? And so I think as soon as you set up an environment where there's uncertain changes to the environment, incoming, threats, if you will, and you've got entities that can replicate and survive, I think you're going to wind up with things that emerge necessarily that have some ability to predict those uncertain, changing environments, and to be able to adapt. And then that meets the criteria of some definitions of intelligence. So,
I mean, I'm not sure that you could think of the Earth without predicting, without agents that predict, like bacteria are enormously efficient at adapting to the various challenges that are uncertain and want to kill them without the ability to predict. I can see the argument that you'd say, well, on Earth, after all, humans emerged, or even let's say big cats or so can also predict the future to a certain degree. They emerged, but I can imagine a world where evolution just doesn't pick that strand of future predicting things in the same pressures.
So I think where I kind of would challenge that is that I don't think prediction is binary, 0 or 1. I think there's kind of a continuum of prediction, and I would personally argue that bacteria as a bacterial system are predicting. They receive some inputs, and they have some coding in there that tells them, I need to swim this way, right? They're not consciously thinking. So I'm not saying they're consciously reasoning, but they are a predictive system in the sense that, when something touches their flagellum or whatever, they've learned or been, programmed by evolution to swim in the other direction. And that's because in the environment, when something touches your flagellum, maybe it's trying to eat you or whatever. So I think they are, we have very tiny, like a microchip that has, 20 circuits that would be considered, or 20 components that we would consider like predictive, right? Like various control circuits and whatever. So it's a very kind of simple and minor form of prediction. And then at the other end of the scale are people. No, I don't think the Earth is predictive. Like, I mean, I don't think the Earth as a whole, the giant ball, like it's not an intelligence because it has no ability to control or react or predict its environment at all. It's just following the simple physical laws. If an asteroid big enough hits it, it's going to melt and end up with just a, new volcanic surface or whatever, or, frozen lava surface. But so my point is just it's a spectrum. And I think that, bacteria are a minor form of, predictive machine.
Let's just quickly finish off with AIXI. This is something that, rightly or wrongly, I don't know why I'm skeptical about this, but AIXI depends on having a computable environment. We've heard so many folks talk about intelligence from a different perspective, whether it's Hawkins thinking about it as a general learning algorithm, or people like Mark Bishop denying computationalism, or people like Melanie Mitchell talking about embodiment, for example. I personally really don't like the idea that you could describe an intelligent agent as literally finding the best computer program that gives you the best reward, whatever the hell the reward is, on all of the previous situations you've been on. I mean, because the result is just a computer program. It has to be a simple computer program, but in the worst case, it could just be almost a memorization saying, like a hash table, saying, in that situation, you should have done this, and in that situation, you should have done that. At least Francois Chollet is talking about generating a new skill program in that situation in response to novelty. But it just seems so reductionist, just thinking of intelligence as being a static program in that particular situation. It's debasing my notion of intelligence.
I mean, maybe that's a personal problem. No, I'm just kidding with you. I don't know. I guess because over the years I became very interested in kind of like different theories of time, like diachronic temporal identity or that sort of thing. I'm not so worried about things being like static per se. I totally could buy the idea that a black box could land on the Earth and be just a bunch of circuits that will never actually change. And yet I would deem that box to be intelligent because it's, just built by some hyper advanced civilization, and it's just that good for the majority of problems. So I think that's kind of the point of AIXI, is that this black box, even though it's static, it's so extreme in its resources, i.e. it can just infinitely evaluate a bunch of infinite things. And sure, once you get to infinities, a lot of weird stuff happens, because at that point, I mean, AIXI is so extreme that, its own evaluation of its own probability of existence would be zero, because it's actually not a computable, like AIXI is implementing an algorithm that's incomputable because of this sort of infinities, right? And yet it assumes that the environment and the reward function is a computable function. So I think that's why it seems a bit weird. It's just because we're dealing with the absurdities of infinities. And I think if you actually have to do something with limited resources, you can't do it with that type of very static, thing. You've got to have something that adapts and forms new connections and whatnot.
Right. But then it gets to the point of it's just it's a mathematical curiosity. It's the same thing as Turing completeness. Right. Who cares?
Well, no, because these things, all these kind of like limiting cases, they're very, very useful for the thought process and design. Like in the case of say,
you sure?
Turing completeness or AIXI or whatever. Well, in the case of AIXI, what it tells you is that the idea of reinforcement learning, that's why I liked so much his thing, that it's the reductio ad absurdum of reinforcement learning. It would tell you that, okay, if we did have infinite resources, this would be an optimal system that solves every reward problem as well as any other, reward prompt could. So then we might know, okay, then it should do pretty well, even if we're only doing a limited resource version. We might be kind of close to optimal. A lot of ways, like,
how is it an optimal system? It's like saying, oh, if I could speak to an oracle and he could tell me exactly what to do in every situation, that's not intelligence.
No, I'm not saying that this is a good definition of intelligence. What I'm saying is that these type of considering the limiting cases are very useful pragmatically, even though they're theoretical constructs.
I don't think they are. So similarly, there's a first step fallacy in AI, which is that, assuming that things that we're doing now, if you keep doing them, they'll get you closer to AI. But I think the first step fallacy also works in reverse. So if you go from this ridiculous notion mathematically of AIXI and thinking that we can step backwards from that and it would give us any reasonable intuition about how to build AI, I think that's flawed.
I mean, you might be right, but let's take a simple example from one of our prior shows that we know is not really flawed. The multi-armed bandit, where we were talking about if you have these results, these asymptotic results that have optimality. Okay, so as n goes to infinity, this procedure is optimal. What use is that in practice? Well, if you can show that those limits are tight enough, right? If they start to become optimal with very few samples, like 100 or 1,000 or something, that even though that algorithm, we don't have a proof that algorithm is optimal for small cases, knowing that it's optimal asymptotically and that it has this kind of